All right, let's go ahead and get started. So my name is Stephen Braun. I work here at Northeastern in the libraries. My full title is Data Analytics and Visualization Specialist, which is a long, fancy way of saying that I provide support to students, faculty, and staff on campus on anything related to data analysis and visualization, very broadly defined. I do that through three main activities. One is through consultations. I'm available as a consultant. I meet one-on-one in groups to sort of answer questions about data visualization, data analysis, things like that. I also do design work, programming work. I work as a designer, as a developer, analyst on a variety of projects. And then finally, I do teaching. So I do guest lectures and courses. I do workshops like this today. I also teach at the School of Journalism. So I do a bunch of different things on campus, all related to data visualization. I'm also the Associate Director of this Northeastern University Visualization Consortium, which is a cross-departmental, cross-college initiative to bring together a community of practitioners on campus around data visualization, to bring together all these different populations who do visualization work together through lectures, symposia, special workshops, things like that. So I spend a lot of time thinking about visualization and sort of what makes good visualization and what makes bad visualization, and sort of a lot of different disciplinary lenses. So full disclosure, I used to be a biophysicist. I'm no longer a biophysicist, but I have that background. Most of the visualization work I do now, and design work, is in digital humanities, arts and humanities, social sciences kind of visualization, not so much in the natural sciences anymore. But I still spend a lot of time thinking about visualization across all these different kinds of disciplines. So one of my arguments is that we all have intuitions already about what makes good visualization and what makes bad visualization. So I could, for example, show you this visualization and ask you, regardless of whether or not you understand the subject matter, do you think this is good or bad? And you might say, it's maybe visually interesting to look at. It's sort of interesting geometries, sort of captures my attention, but doesn't really encode much useful information in a way that really makes it very readable. So you might say those kinds of things. Likewise, I might show you this visualization and ask you the same thing, regardless of whether or not you understand the subject matter, if you think it's good or bad. And you might say, wow, it's a lot to look at, right? So it's not very good from a readability perspective, but it encodes a ton of information. There's so much embedded inside this figure, right? So you have these trade-offs and these intuitions that we have about good or bad visualization. So I would argue that there are ways that we can surface these intuitions about good and bad visualization by leveraging principles of information design. So by information design, I mean something along this kind of definition here. So the use of visual encodings to represent information or data in a way that facilitates exploration, discovery, and analysis. So there are three key points to this definition. The first is information, right? We can't have data visualization if there's no data to begin with. And here, information is a very broad definition of data. So data looks like something different across different disciplines, right? Look like something specific to your discipline and look completely different to a different discipline, right? So data can represent a wide variety of media modalities. Second key point is visual encodings. So the whole point of visualization is that we're taking data or information and transforming it into something visual, something that we can read and consume with our eyes. And then finally, this facilitation aspect is also very important, because a visualization is not useful if it doesn't facilitate exploration, discovery, and data analysis. So the way that we define information design and visualization is important because it means we can think about visualization in a couple different senses. So we can think about it first as an object, sort of the charts and graphs that we call visualizations. So for example, bar charts, scatter plots, line charts, right? They're the things that we call visualizations, they're the things that we make as visualizations. But we can also think about visualization as a process of scholarly inquiry and analysis. And once we start thinking about it as more of a process and less as an object, we can situate it within a larger pipeline of activities that we're much more comfortable working with. And that pipeline ranges from data collection all the way through interpretation. So this situatedness of visualization right here between analysis and interpretation is actually very important, because it means that we can think about visualization not only as an analytical tool, but also as a rhetorical tool. So what I want to do is spend some time, the next hour and a half, 2 hours, talking about these different intuitions that we have about data visualization, and sort of coming up with some practical tips for how to surface those intuitions in your creation and your interpretation of visualizations yourselves. So I want to start with a bit of a warm-up, get you thinking about the intuitions that you already have. So what I want you to do is to break up into small groups, 4 to 5 people, And in your small groups, I want you to find 1 to 2 examples of what you would consider good visualization, and 1 to 2 examples of what you would consider bad visualization in the scientific literature. So these could be charts or graphs that you've seen in recent articles that you've read. It could be something that you've worked on yourselves. Just find 1 to 2 examples of each good and bad visualization. And then once you identify those visualizations, I want you to come up with some generalizable criteria to justify your evaluations. So what makes a good visualization and what makes a bad visualization? Try and be as specific as possible. So I'll give you about 10 minutes to work on this in your small groups. So go ahead and find your visualizations. Okay, let's come back together. So let's just discuss briefly what you found. So what kinds of things, what kinds of properties make a good visualization? What kinds of things did you find? Yeah.
Good composition that immediately draws your attention to the most important features.
Good composition that immediately draws your attention to the most important features. Very good. What else? Yeah.
In our group, we decided like some form of interactivity. If it's interactive, it really helps get a sense of the figure.
Yeah, so interactivity is useful because it gives the user some control, and it facilitates that sort of data exploration that was part of that definition too. That's good too. What else? Yeah.
Also by interactive we meant, suppose we like in the tableau, when we have a point, we hover the mouse over it and it gives other metadata about
Right,
the point.
right.
So we can identify that point very easily.
Great. What else? Yeah.
Every element in the figure actually conveys some information to something ancillary about all the colors or groups to something that points to lines or correlates to some kind of data.
The encodings are succinct, right? They are appropriate, they are relevant. Good. That's a very good observation too. Anything else? Okay, what about things that make a visualization bad?
It's easy to be too clever.
Say that again?
It's easy to be too clever.
What do you mean by that?
Well, you were pointing out one that's just like, well, we need to show all these things and I don't really know what to do, and so you put it together in some kind of clever plot that is impossible to comprehend. And you could, I mean, there's probably gradations of that, but you can easily take those in.
So choosing an inappropriate way to visually communicate data that sort of reduces readability. What else? Yeah. Too many variables, too many plots, there's too much going on. What's that?
The clutter with the plot.
Cluttering, yeah. Yeah.
Counterintuitive and misleading plots.
Misleading plots, yeah. Anything else? Yeah.
If the scale is off, the scalability of it, you don't get a proper sense of magnitude.
Right. So issues with scale, which relates to issues of encoding as well. Yeah.
Improper labeling of the axis or no labeling at all of the axis and the legends.
Right. So axis labels, legend labels, and its relationship to legibility. It's probably much easier to come up with things that make a bad visualization than things that make a good visualization, right? So I think we are all very much attuned into identifying when things are not good, right? So what I want to do is spend some time in the next hour or so talking about some of the points that you raised, and specifically talking about how they relate to improving the effectiveness of visualizations, okay? So this is going to be a general overview, a general survey of information design principles that we can leverage in improving the effectiveness or clarity of a visualization. We're not going to go into great depth on these topics, but my hope is that they'll give you some practical tips, practical tools that you can implement in the visualization you create yourselves, or whenever you're reading somebody else's chart or graph. So I'm going to talk briefly about these 4 aspects of improving effectiveness. First, I'll talk about composition, using hierarchy to improve layout and flow. Then I'll talk about color, the very important topic of color that you can never avoid when talking about information design, and how we carefully select color schemes. Then we'll talk about figure clarity, emphasizing visual and interpretive salience. And then finally, we'll talk about dimensionality in terms of reducing variables to simpler views. So a lot of the content for the slides that are to come are actually derived from Nature Points of View, a collection of articles, short articles about information design, data visualization principles, specifically applied in the biosciences. So if you're interested in learning a lot more about the things that we touch on today, you can go to this link at the very bottom here. There's tons of short articles about a bunch of different kinds of topics, ranging from Gestalt principles all the way to typography, use of typography in charts and graphs. So it's a wonderful resource for finding more information about these things. So I'm going to start by talking about composition and hierarchy, which is one of the things that you mentioned actually makes a good visualization, right? You know visualization is good when the composition sort of draws you in and sort of guides your eyes through the visualization. So when I say composition, I'm referring to the visual layout, the visual arrangement of elements on a page, elements in a figure, in a chart or graph, okay? And this is important because effective layout really determines what's called hierarchical organization, which guides the eyes of the viewer. So we can think about composition in both general and specific terms. We can think about generally in terms of the overall layout, the overall arrangement of materials in a figure. But then we can think about more mechanistically in terms of hierarchy. And this idea of hierarchy is going to be a recurring theme through all of these different facets of effective visualization design that we're going to talk about. So the key idea here is that complex information, when presented with good composition, can be more easily understood. It's more readable when it's laid out effectively. So there are two key ways that you can build good composition into a chart or a figure. And those are using grids, grid layouts, as well as using ample white space. So the top part of this figure right here shows a couple examples of using good grid layouts to organize material in a poster. So we see the grid layouts in the background in both of these poster examples. And all of the blocks of content are aligned according to those grid lines. Right, so we're familiar with this, right? We do this kind of stuff all the time. We work with alignments and work with grids like this all the time. But we maybe don't always think about very intentionally. Closely related to that is the use of white space. So in this example right here, we have these different blocks of contents in gray, these gray blocks. And we have this sort of path that's drawn out for us that goes from this point to this point, all the way through the rest of the content. And this path right here is sort of the natural path that our eyes will follow when reading a poster that's laid out in this way. And our eyes will follow that path because of the use of white space. So there's ample white space between these two. If we think about this as a block of content and this as a block of content, right, we have this chunk of white space between them that sort of thematically groups the elements, the blocks inside of the larger blocks together as being part of one thematic group. And we have the same thing over here where we have ample white space between this block, this column of content, and then these two blocks over here. So the use of white space can actually have a very dramatic effect on how we interpret and understand a figure. So don't forget that you can always use that at your disposal. Here's an example of a poster that has actually been improved using grid layout and white space, improved its readability. So the top figure is the original poster. If we represent that poster in terms of blocks of content in part B right here, so every gray block is a block of content, could be a text content, could be an image, could be a figure. If we look at sort of the overall distribution of those blocks of content across the poster, we don't see a whole lot of alignment. We don't see good use of white space between the blocks of content. And it's really kind of difficult to figure out the order in which we're supposed to read the content, right? If we're thinking back to this order right here, we don't get that same kind of clean pattern when looking through this schematic of the poster. In part C, we've improved the use of alignment and grid layout as well as the use of white space. So now that there is sort of a logical order in which we're supposed to read the content. We start in the upper left hand here, we go down the column, we move to the middle column, and then we finish up with the remaining blocks of content right there. So again, this use of grid layout and white space can have a dramatic effect on how we interpret and read a figure or poster. So the reason why this stuff works is because of something called Gestalt composition. Raise your hand if you've heard of Gestalt laws. A couple of you. So you may have heard about Gestalt laws in the context of art theory. So this is sort of a collection of perceptual organization rules that we follow as human beings in terms of our human psychology, in terms of how we interpret visual spaces. So it's a collection of perceptual organizational rules that determine how we interpret visual spaces. So there are a bunch of different laws or principles, so to speak, similarity, proximity, closure, provenance, and isomorphic correspondence. And each of these has some role in data visualization and how we interpret a visualization. So here are some of the principles in more detail. So the law of proximity says that objects that are close to one another in a figure are grouped together as being part of a single thematic unit. So we see with these collections of circles right here, all of these circles are very close to one another in this group right here, so we might identify this as one single unit, one thematic unit of content. In contrast, down here we have these three different rows of circles. So we might view this particular row as one unit, this particular row as another unit, and another unit down here, right? But we wouldn't merge them all together as a single thematic unit altogether. So that's law of proximity. Law of similarity says that objects that look alike are grouped together as thematic units. So here we have our circles again, and we have different visual appearances to these circles. So this top row of circles all looks the same, so we might group that together as one unit. This next row looks the same, so we might group that as another separate unit. Same with the remaining ones, and then finally we end with this row of squares, which sets it apart even further from the preceding rows above it. So law of similarity says that things that look alike are often grouped together in our perception. Law of closure, so interrupted geometries become closed in perception. This is possibly an optical illusion you've seen before, right? There's actually no triangle here, but the cutout shapes make it look like as though there is a triangle, so our perception closes that shape for us. So this actually has a role in visualization, especially when we're working with line charts, and there are breaks in line charts. So it's very important always to encode what those breaks mean. Otherwise, our perception will naturally link end-to-end those breaks in line charts, and that might result in unexpected interpretations of our visualizations. Figure grounds, another popular optical illusion you may have seen, right? Is this two people looking at each other, or is it a candlestick? We'll never know. This idea actually plays another role in visualization. I'll show you an example in a couple slides. Continuity, interrupted paths remain connected in perception. So if we have two paths that cross each other, we still recognize them as continued paths. And then common fate, objects that move in the same direction are grouped together. So this is common with animation-based visualizations. So these are sort of low-level Gestalt principles of perceptual organization. And then we have higher-level principles, like isomorphic correspondence and the law of provenance. So isomorphic correspondence basically just says that when we interpret a visual space, when we interpret a visual figure, we rely on our past experience, our past associations with other things to interpret what's going on in that figure. So a popular example is the use of red to encode negative things and the use of green to encode positive things. So we think about a stoplight, for example. Red means stop, green means go. Same thing with a bar chart, for example. If this is a chart showing profits or losses for a company, we might color the profits bars, the positive profits, as green, sort of tying in that association with green being good, or green being positive. And then the red bars indicating the negative values for the losses. So that same association right there. So that's law of isomorphic correspondence. And then law of provenance basically says that cognitive load is reduced by reducing things to the simplest form, which is really just a fancy way of saying simplify your charts as much as possible to aid perception, to aid interpretation. So a very common example of this is you might have a bar chart that looks like this. Maybe you have a categorical variable on the x-axis right here. A very simple thing you can do is to order those bars in descending order by magnitude, right? Because then that facilitates easy comparison of the bars, easy comparison of other kinds of measurements of the charts that really enable the interpretation of that charts. So law of provenance, reducing things to their simplest forms. So let's see an example where these laws of perceptual organization can make or break our interpretation of a visualization. So in panel A, we have at the top, we have a couple of square points and a couple of circle points. So the law of similarity might tell us that we want to group together the squares and group together the circles, right? Law of similarity says similar looking things are grouped together as a thematic unit. In the next panel right here, we now have drawn a line between the squares and the circles. And so the law of proximity might tell us that maybe this relationship is more important than the square and circle symbol relationship. And then finally down here, we've increased that association even further by drawing an enclosure around this particular circle and this particular square. So now it's not so much the proximity that's enforced by these lines, these connecting lines right here between the circle and the square points, but there's something important about the proximity of this circle point and this square point right here, and that we're just calling out by using this enclosure around it. So ways that we can make or break sort of perceptual organization, perceptual interpretation of a visualization. In B, we have a similar effect, where in the first example here, we have just randomly positioned points. We have circle points and we have square points. And the law of similarity might tell us to group together the squares and group together the circles as before. But the law of proximity might tell us that maybe the proximity of these points over here is important, right? Maybe they're close to each other and that's important. We can reinforce what kind of pattern we want the user to actually understand by just drawing lines between the points. So now we've drawn lines between all the square points and drawn lines between all of the circle points, reinforcing that law of similarity. And maybe we've added a call out up here to specify that this particular association, that particular cluster of points is something that we should pay attention to. So ways that we can make or break interpretation. Here's an example of how figure and ground can play a role in visualization. So this is a fairly famous visualization in the visualization community because it's a very bad visualization. You may notice right away that the vertical axis right here starts at the top and ends at the bottom, so our vertical axis has been inverted. And we've added this very strong red background color, this red fill color, to turn it into an area chart. Now this is problematic because, for one thing, since our vertical axis is inverted, it looks like after this Florida enacted its standard ground law annotation as noted here, there's a sudden drop in gun deaths. But actually the inverse is true, right? Because the axis has been inverted vertically. It's also problematic because the figure-ground relationship is ambiguous here, right? It's unclear if we should be reading this as the figure, sort of looking at this white space down here as representing the figure, or if this red part, this red region, should be the figure. So this visualization actually plays a lot with our interpretation in ways that are not good. So this is sort of an example of how figure ground can actually play a very important critical role in how we interpret a visualization. Another thing that we can improve upon when talking about composition is composition through typography. So we can really use typography and text to organize the visual space in the figure and guide the eyes of the viewer. So we can do that through a bunch of different aspects of typography, so things like font size, typeface, weights, color, orientation, space, and alignment. So in this example here, we have at the top difference in font size. Here we have another difference in font size. Here we have a change in indentation or alignments. So all these different kinds of examples of typographic properties that are sort of guiding the eyes of the reader through the context of the slide. So here's an example of that in action. So this, if we look at these two examples up here, A and B, so these are a couple of bulleted lists that may be in a paper, for example, or maybe part of a figure or a poster. And the typography, the organization of A is not so good if we look at the sort of the use of white space and alignment down here. So we see that, for example, with the unjustified text, we have this jagged outline, this jagged edge that sort of spans across the entirety of that block of text. That's sort of jarring for the reader to read that content. And we also see that there's sort of inconsistent use of carriage returns in between the contents here, inconsistent use of white space to separate the contents between those bulleted points. The example in B improves upon that by justifying the text. So now we have a much smoother outline, smoother edge to that block of text. And now we've used some more consistent indentation and spacing and alignments to make this bulleted list stand out a little bit more clearly, a little bit more indented from the main block of text above it. So typography is another really easy way that we can improve composition in a figure. Any questions about any of that? So that's composition. So the next thing I want to talk about is color. So color is one of those very important things that we maybe don't spend enough time talking or thinking about when we're creating visualizations. So this is important because color serves a lot of different purposes for us, right? Color serves to label and classify, to measure, to represent reality, and also just to decorate. But because it plays all these different roles, that means it's very, very important in our perception of color. So we need to be very particular in the ways that we choose our color palettes in a figure. So a good starting point when talking about color is to discuss sort of different models of how we represent color. So the most common way that we represent color is through this model right here. So we separate color into lightness, or the amount of white or black in a color, hue, which is the name of the color, red, green, blue, purple, things like that. And then saturation, which is the amount or quantity of that hue relative to black. So we tend to think about colors in this sort of model right here. And this model really reflects human perception, the way that humans understand and interpret color spaces. Now this is important because computers do not often think about colors in the same space. Computers tend to think about colors in terms of red, green, and blue. In terms of how much red there is in a color, how much green there is, how much blue there is, and separate colors out across those different categories. So this is important because what can result is what's called non-perceptually uniform color palettes. Non-perceptually uniform color palettes. So let's see what this looks like. So in this top example right here, we have a monochrome gradient from black to white. And in this gradient, because it's monochrome, every step in color right here is equal. So we can compare any two adjacent steps across this entire color palette, and we would be able to measure the lightness and differences of lightness, and all those differences would be equal in size, equal in magnitude. But when we start trying to do that kind of thing with a non-monochrome color palette, we start running into problems. So this is a rainbow color palette. So you may have heard that rainbow color palettes are horrible for visualization. And one of the reasons is that a rainbow color palette is non-perceptually uniform, which means that steps in colors in the rainbow color palettes do not always correspond to equal steps in data when you're using that color palette to represent the data. In particular, we tend to see a sort of increase in intensity right around this yellow region right here. So humans are unusually sensitive to the color yellow. So what happens is that it almost looks like there's this arbitrary boundary that's being enforced right here, right? So we see that the gradation in color on either side of that is not equal compared to the remainder of the color palettes. So we're unusually sensitive to the color yellow. So this is why we sort of get these non-perceptually uniform color palettes. And these are things that we have to avoid when choosing color palettes for our visualizations. So how do we choose good color palettes? Well, a good color palette should do a variety of things, but it should really bring unity, identity, consistency, and hierarchy to a visualization. So that idea of hierarchy is coming back into play again. And importantly, when we're choosing color palettes, we need to be very careful of default color palettes. So this is especially true because the vast majority of the time we're creating visualizations using software. And that software may have particular ideas about what makes a good color palette for your visualization, but that may not have your best interests in mind. So we always have to work up and against these default color palettes that software offer us. And it's really up to us to choose appropriate color palettes, color schemes. So what makes a good color palette? A variety of things. So the first thing is that we use colors that are easy to distinguish. So this seems pretty intuitive, right? It seems like something we shouldn't have to specify, But we see this being violated all the time in visualizations, where people are choosing color palettes that are not easy to distinguish. So here's an example of what that looks like in action. So the top color palette up here consists of 4 colors that are reasonably easy to distinguish, right? We can tell the difference between this color, this color, this color, this color. The bottom color palette right here is the same color palette that's been interpolated to 10 colors. So I've just taken the extremes of the top color palette and then spread that out over 10 colors. And we see that it's much more difficult to tell the difference between, for example, these 2 colors than it is to tell the difference between this color and maybe this color down here. Whereas up here, we can tell the difference between any pairs of colors in that color palette, right? So choosing color palettes that are easy to distinguish means not choosing color palettes where it's really ambiguous what the difference between any two pairs of colors is. So in general, use a total of 4 to 6 different colors. That's the ideal number for a color palette. Really no more than 12. If you have to use more than 12 colors in a color palette, reduce the complexity of your data classes. So transform your data into fewer classes so that you can use fewer colors. Okay? So use colors that are easy to distinguish. Other thing that makes a good color palette is using colors that are accessible. So I mean this in 2 different senses. I mean this both for color blindness purposes, but also for people who do not have color blindness. So let's talk about color blindness first. So here on the left, we have a color palette, sort of a rainbow color palette, that's been transformed into one form of color blindness in the middle here, and then grayscale on the right. And we see that when we transform into both the colorblind palette as well as the grayscale palette, we've lost a lot of detail that's available in the original palette, right? We've lost sort of a lot of the detail on this end of the spectrum, over here as well. A lot of these look very similar in class. So we haven't chosen a color palette that is very effective across both colorblind needs and grayscale needs. Here's an example of a color palette that is colorblind friendly. So the top one is an example that's not colorblind friendly, first of all. So the original color palette is up here on the top band. And then the band right below it is what it looks like to someone with color blindness. So we've taken a diverging color palette up here, and we've completely lost the poles. We've lost that divergent quality in the color palettes for color blindness. Here's another version of a colorblind friendly palette. So the original palette is up here. Here's what it looks like to someone with color blindness. So we still have a divergent color palette in both examples, right? So we haven't lost the data detail that was embedded within those color palettes. So choosing color palettes for colorblind needs is a very important thing. But it also applies to people who do not have color blindness. So here's one of my favorite visualizations to show when it comes to talking about color. So this is a map of the United States, colored by county, and I have intentionally removed the key, the legend from this map. And so if I were to ask you what is most striking about this visualization without looking at the key, what might you say about this visualization? What is it trying to convey?
Great division between one side.
Yeah, so it looks like there's this big division right in the middle of the country that splits the country east and west, right? We have these blues and greens, this cool blues and greens, and then these warm oranges and yellows and reds on the other side of the country. Now, if I throw the legend back in, we see that every step in color is supposed to represent an equal size step in the data values. So if we go down here to where we have this green to yellow transition right here, right? Each of these steps in the colors are equal, but perceptually, it doesn't appear to be equal, right? And that's again because the rainbow color palette is not perceptually uniform. So this barrier appears right here because we're unusually sensitive to the color yellow, and that contrast between the yellow and the green right next to it makes it look like there's this big division right down the middle of the country. So again, using appropriate color palettes that are not only useful for colorblind people, but also for people who don't have color blindness is a very important consideration to make. So how do we choose colors that are accessible? Well, first we can start off by emphasizing colors that provide strong visual contrast, and selecting colors that vary mainly in brightness over hue. So humans are better at interpreting changes in brightness or lightness in colors than they are in detecting changes in hue for colors. So it's better to choose color palettes that vary mainly in their brightness than they do in their color names. And then finally, when appropriate, if you don't need to use color, don't use color at all. Find other ways to encode your data so that you don't have to worry about working with color and choosing accessible color palettes. Another thing that makes a good color palette is using colors that are semantically relevant. So this goes back to the idea of the law of isomorphic correspondence again, that Gestalt principle that says our interpretation of a visual figure is based on or related to past experience of other associations we might make with that figure. So semantically relevant in this case means doing things like choosing red color to represent negative values, and choosing blue or green to represent positive values. Right? They're semantically relevant. They're semantically relevant to our past association with those colors. But it also means using color palettes that are relevant to data and sort of the behaviors of data, the types of data that we might be working with. So a good starting point to talk about this is to note that there are three main kinds of color palettes that we're often working with. So the first is a sequential color palette. So in a sequential color palette, we're typically encoding data that increases or decreases linearly in one direction. So this might be the value 10, for example, and this might be the value 0. So we go from 0 to 10 with the sequential color palettes. A diverging color palette is one in which there are two poles, two polar opposite ends in our data sets. So here we might represent this as a positive 10, this as a negative 10, right? The red value indicating the negative values, the green color representing the positive values. And then finally, in a qualitative color palette, we typically have classes of data. We have categories, right? We might have ordinal data, we might have nominal data, but we vary mainly in hue, in color name, than we do in brightness or lightness across those color palettes. So when we're choosing color palettes, we should choose palettes that match the kinds of data that we're working with, right? If we're working with data that vary linearly in one direction, we should choose a sequential color palettes. If we're working with data that's purely qualitative, where there's no ordered sort of relationship across the variables, then we should be using qualitative color palettes. And if we're using a qualitative color palettes, then we should really emphasize palettes that only show contrast between classes and not order of magnitude. So that means we should use variations in hue and not variations in lightness, except when we're working with ordinal scales. So let's see what this means with a practical example of a commonly employed color palette that's not actually very good for qualitative color palettes. So here are three different palettes. They're all qualitative in nature, and they're all supposed to represent qualitative data. So at the top here, we have a bunch of different hues, right? We have this blue, orange, green, red, purple, etc. And each of those hues is paired with a similar hue in a different lightness, right? So we have dark blue, dark orange, light orange. That's extended down here with these purples and these greens and these blues and these oranges, right? So we have to be careful about using a color palette like this with qualitative data, because if our data is truly qualitative, then there's no relationship across the variables. And the problem with these color palettes is that these variations in lightness between the hues implies that there is a relationship across those categories. It implies that there's an ordering, a natural ordering between these four lightnesses of purple or these four lightnesses of blue. So we have to be very careful about how we're choosing our color palettes and making sure that they're matching the variety of data that we're working with. So that's semantically relevant color palettes. Another thing that makes a good color palette is using colors that minimize perceptual interactions. So this is actually one of my favorite things about color, working with optical illusions and figuring out how to avoid optical illusions. So the two most common optical illusions that come into play when we talk about color, that come into play with visualizations, are simultaneous contrast and contrast of hue. So in simultaneous contrast, we might have a bar of a consistent color in the middle of a gradient that's changing color in the background. So this bar in the middle is actually the same color all the way throughout, but it appears to be changing in lightness or in saturation as it moves against that background with that gradient change. Contrast of hue is similar, except it focuses on sort of the increased salience of particular hues when they're matched against other background hues. So for example, this blue looks very intense when it's pushed against this bright yellow. Or same with this yellow looks very intense when it's pushed against this black background. So we have to be very careful about how these different optical illusions can actually influence the way that we're interpreting and understanding colors in our visualizations. So here's an example of contrast of hue in a heat map. So who can tell me what's wrong with the color palette in this heat map? What's that?
Could be a little bit more stretch in our lower.
Yeah, so
Give you better information.
So it's not, the color palette is not evenly distributed across this range, right? We have sort of this very condensed blue region and this very elongated yellow to red region right here. And the consequence of that is that all of our reds and our yellows really pop out against those blues, those dark blues. And they might imply very strong associations that may not actually be there in the data. They might sort of imply that these are points of significant salience that we should really be paying attention to, when in fact they could be down here in this lower region, right? So that contrast of hue is coming into play in how we interpret the heat map. Let's look at a couple more heat maps. So if I were to show you this heat map and ask you, is this heat map better when it comes to perception and interpretation? Or is this heat map better when it comes to perception and interpretation? Which one do you like more? Do you like number 2, or do you like number 1? Raise your hand if you like number 1. Raise your hand if you like number 2. So why do you like number 2 more?
At least it has this scale of color coding.
So okay, so ignoring that. So that is a major flaw of this one. There's no legend. But ignoring that, why else would you like this one more than the other? Yeah.
And it's really easy to blend out all the white parts, where there's probably nothing interesting going on.
Yeah, so this goes back to this idea again that as humans we're better at interpreting or noticing differences in lightness than we are in saturation or hue. So this use of white actually makes it much easier for us to tell the difference between data cells at this lower end of the spectrum, right around this center point right here. Whereas we wouldn't be able to do that so easily in this example, because those very small values would be washed out by the very dark colors. So again, this use of lightness is actually better when it comes to human perception. One more example of a heat map. So if I were to show you this slice of a heat map and ask you, is the top asterisk cell darker or is the bottom cell darker? Which one would you say is darker? Who says top is darker? Who says bottom is darker? Okay. So it turns out these are actually identical. They're the same color. So what's happening here is actually that simultaneous contrast. It's the actual optical illusion that's coming into play when we interpret this heat map. So you may not even be aware that this is happening all the time when you're creating heat maps, but it is. the simultaneous contrast problem. So we have to be very careful about the color palettes that we choose to really minimize this illusion that there are differences in these two colored cells when they're actually the exact same. So there are a couple of great tools that can help you choose good color palettes for your visualizations. The first one is called Color Brewer. So this is a tool that was originally created for cartography, for choosing color palettes for maps. But it's a collection of perceptually uniform color palettes. So someone has done the research, someone has done the work of figuring out these color palettes that are perceptually uniform. And it also includes colorblind safe palettes. So what you do is you start at the top and you select the number of data classes in your data sets. Then you choose if you're working with a sequential, diverging, qualitative data sets. And then you choose your color palette right here. And you have the option of selecting a colorblind safe color palette right here. And it gives you the options, the colors, the hex codes, and you can export them to Adobe products or to JavaScript, or just get the hex codes that you can use in R, for example. So this is a great tool. There's also an R package for Color Brewer that you may talk about. I'm not sure if you will or not. But it's a really easy way to just pull these color palettes directly into anything you create in R. And one more tool I'll mention is this one, which is a tool for checking for color blindness for any figure you create. So what you can do is you can upload an image to this tool, and you can check what it looks like across all these different kinds of color blindness, all these options up here. And it's a really easy tool for checking to see if something you just created is something that someone with color blindness can actually read and understand without there being any loss in encoded information. Okay. Any questions about color?
Have
Yeah.
you used like the I1Q site?
I'm not familiar with that one.
I1Q.org.
Okay. Is that another color palette chooser site?
Yeah, but it gives you a lot of, I can't always tell them apart, but I didn't know about Color Brewer too, and I'm trying to find palettes for color.
Okay. Yeah, there are lots of tools available out there. One of the things I like about Color Brewer, again, is that it's perceptually uniform color palettes, and it's very easy to just export those color palettes into any other tool that you're working with. Okay. So that's color. Next thing I want to talk about is figure clarity. So this refers to the readability and the legibility of a figure. So before we talk about figure clarity, we need to talk about what makes up a visualization, sort of the anatomy of a visualization. So typically speaking, we can break down a visualization into three parts. The first is marks, which are the basic graphical elements or primitives in the visualization. I'll show you what that means in a moment. Then we have channels, which are ways to control mark appearance. And then finally, we have attributes, which are the dimensions of data. So sort of this marrying of our data values with the actual visual elements in a figure. So when we talk about marks, we're typically talking about these kinds of things. So things like points. So these are the kinds of marks you'll find in a scatter plot, for example. Lines, you might find that in a line chart, but lines also refers to bar charts. That's the mark type used in the bar charts. Areas, we use those in area charts. And then we also have these higher level kinds of marks, which are containments and then links. So you might see these kinds of things in network diagrams, for example. So these are all examples of marks, the graphical primitives, graphical elements of a figure. So once we have our marks, we can then modify their appearance through what are called channels. So these are things like color, value/gradation, texture, symbol, sequence, size, and scale, things like that, that allow us to change the visual appearance of the marks, and that allow us to encode data through those appearances, through the marks. So if we have some example charts like this, in this first example here, the mark is a point. All the marks are points. And the channels are position, X position, and Y position. So that's how we talk about marks and channels in visualizations. In this one, the mark type is a line or a bar. And then the channels are X position and then length, vertical height or length. And then finally in this one, the mark type is points. And we have a few different channels. We have X position, we have Y position. We also have circle size, point size, and we have point color. So these are all different ways that we can encode data through the visual appearance of these marks using these channels. So having an understanding of this terminology and sort of this language for describing or deconstructing a visualization is important, because it means we can start thinking about how to improve the readability of a visualization. So one of the classic sort of mantras of data visualization comes from a guy named Edward Tufte, who wrote this book called Visual Display of Quantitative Information. This is a very important book in the field of visualization. If you're not familiar with it, I highly recommend you find a copy for yourself. And Tufte is known for saying a lot of different things, but one of the most important things he says is, above all else, show the data. So when it comes to creating a visualization, a chart or a graph or a figure, when we're choosing our marks and channels, and we're choosing how to build up the figure, we should really emphasize only those marks and channels that actually directly encode information, encode data directly. So he has this notion, this idea related to this mantra of the data ink ratio, which you may have heard of if you are familiar with Tufte's work. And the data ink ratio is sort of this fictional ratio of data ink, which is the amount of ink used in a graphic that directly encodes data, divided by the total ink used to print the graphic. So the ideal here is that we want a data ink ratio that equals 1, where all of the ink used to print the graphic directly encodes data. So let's see a couple examples of this where data ink ratio is high and where it's low. So we'll start where it's very low. So here's an infographic about fantasy sports. The data ink ratio for this is very low because there's just a lot of ink in this graphic that does not encode any information whatsoever. Right? We have this background ink up here. We have these flags up here. We have these icons of people that may or may not encode information. It's really ambiguous at this point if they represent a particular data point or not, or if the triangles represent the data point or not. So Tufte would say this has a very low data ink ratio, and as a result is not a good visualization. It's not a good infographic. Contrast that with something like this, which has a very high data ink ratio, right? So we could argue that pretty much all of the ink, any piece of ink that you might find in this graphic, encodes some kind of information about the data. But is this a good visualization? I would argue no. I would say this is actually, for one thing, quite ugly. For another thing, not very readable, because we just have so many overlapping crossing lines here and so many different colors that it's really hard to read. It's really hard to pull out any useful information from it. So the lesson to be learned here is that while the data ink ratio can be a good guideline for understanding how to improve the clarity of a figure, it's not an absolute guideline, right? You can use it to sort of guide us in the direction of improving figure clarity, but it shouldn't be the end all of everything, okay? So just like what we did with color, we have to be careful when improving the clarity of a figure because software defaults are not always our friends. Software defaults will often throw things in our figures that are unnecessary, that don't add any additional value to our visualizations that we can get rid of if we specifically explicitly tell the software to do so. So I have a few examples of charts that were created in R that demonstrates this. So here is an example of a bar chart. This is base plotting in R. And this is not a very clear figure, right? It has a bunch of unnecessary detail. For one thing, it has this grid background, this light gray background that we don't need, that's sort of distracting from the original data. It's also difficult to read down here with these labels for the x-axis. So this isn't a very clear figure, but this is sort of what R might give us by default. Here's another example, a multi-series line chart, where again, we have an unreadable x-axis down here. And then it might be difficult to see, but we have all of these grid lines, these vertical grid lines in the background, vertical and horizontal, that we don't need, that we could get rid of, and that could easily clear up the visualization. Here's an example of a scatter plot. So again, we have the same problem where we have the background grid lines. We also have another problem here where in areas of high density, it's difficult to see the clusters because the circles overlap, and it's difficult to point out or call out the exact numbers, exact quantities of points in those areas. This one could be easily improved by doing something like this. So what we've done is we've gotten rid of the backgrounds, grid lines. We've added this border around the edge. And then we've also changed all the closed circle markers that were over here into open circle markers on this side. So that we can now look at regions like in this area right here and tell the difference between individual points and see those areas of high density. Okay. So we often have to be deliberate in how we improve the clarity of a figure when working with software defaults. So there are a few different ways that we can simplify charts and graphs. The first is to reduce the number of elements. So reduce the number of marks, reduce the number of channels that you use in the visualization. Right? The simpler, the easier it is to read. So don't try and cram too much information into a single chart. We can also use Gestalt principles to really guide the eyes of the viewer through our visualization. So use those laws of conceptual organization like similarity, proximity, isomorphic correspondence to really help guide the reader through a complex chart. And then the final thing that we can do, and probably the easiest thing that we can do, is to just use strong visual encodings. So strong contrasting encodings really enhance the salience of particular data elements in a chart or a figure. So what do I mean by salience and using strong visual encodings? So consider a figure like this where we have a protein sequence. And we are asked to point out or call out all the instances of A in this sequence. So we can see that the A's are very clearly highlighted in red here. Right? Here's an A, there's another A, another one right there. But if we were to contrast that with another task where we're supposed to call out or find all the P's in the sequence, that would be a much more difficult task. And that's because the salience of the P's is not as great as the salience of the A's are made through this use of color to increase their visual sort of forwardness in the figure. So there are examples of strong visual boundaries that we can use when selecting particular markers for a figure, and there are examples of weak visual boundaries. So strong visual boundaries include the ones at the top, this top row up here. So things like matching circles with crosshairs, right? So it's easy to tell the difference between those two different kinds of points in a scatter plot, for instance. Or doing the same thing with crosshairs and squares. We can do similar things with color, so using contrasting hues to increase the salience of particular data elements in a particular visualization. These are all examples in the second row of weak visual boundaries. So these are examples of symbols that are difficult to tell the difference between them. So here we have two different kinds of triangles. Here we have a right-facing triangle matched with an up-facing triangle. It's very difficult to tell the difference between those two different kinds of triangles. They look very similar. Same thing with triangles versus diamonds, or squares versus diamonds, or these other shapes down here. So we should try and avoid these examples of symbols that have weak visual boundaries, or combinations of symbols with weak visual boundaries, and really emphasize these examples that have strong visual boundaries. Another very simple thing that we can do is, when we're working with symbols, always choose open symbol markers as opposed to closed symbol markers. For the same reason that we saw in that previous R example plot, that scatter plot. So open markers allow us to tell the difference between individual points in a cluster points, right? Whereas, for example, down here with the closed symbol markers, we can't tell exactly how many points are in this region right here, or this one right here. And above that, if you're to choose a particular symbol for a visualization, and you're going to choose an open symbol marker, you should always choose open circle markers over other shapes. And the reason is that the circle is the only shape that doesn't repeat itself when it overlaps. So when these circles up here overlap, we don't get more circles on the inside, but we do get more triangles when these triangles overlap. We get more squares when these squares overlap, and we get more crosshairs when these crosshairs overlap. So sort of the default best option for choosing symbols for a chart are open circle markers. So here's an actual example of a scatter plot and an improvement upon that scatter plot. So if we look at this example right here, this is kind of difficult to read, right? And it's because there are a couple things going on. First of all, we don't have simple markers with strong visual contrast between them, right? Our clusters are being identified with these diamonds, squares, and upward and downward pointing triangles. So it's just a lot of different angles that are being clustered together, and it's difficult to tell the difference between them. And also these colors are not very useful for telling the difference between these mutation states. This is an improvement upon this example in A, where we have now clusters indicated by color, and now we've reduced our data classes to no mutation versus mutation 1 or 2, and we're using one kind of symbol marker, a circle, across the entire chart. And then here's another example of that where another kind of strong visual boundary symbol marker is used, where instead of using just all circle markers, we're using orientation now. So we have horizontal lines versus vertical lines to represent the difference between the different mutation types down here, 1 and 2. Here's another example in A of a chart that is a little difficult to read, especially in these regions of high overlap right here. So it's kind of difficult to see how many points there are exactly in this region right here. And up here we have a lot of awkward overlap across these different kinds of points. In B and C, we've improved the appearance of those regions of overlap right here, where it's a little easier to tell how many points are there, what kinds of points they are. Down here, again, we're using open circle markers, things like that. So these uses of different kinds of markers can actually have a dramatic effect on how you interpret a visualization. The last thing I'll mention about simplifying charts and graphs and improving figure clarity is typography. So again, that's coming back into play here. So using consistent alignments of labels and callouts can actually play a big role in how we interpret a visualization. So we probably have seen lots of examples like in A, where it's a scatter plot and it's impossible to tell which labels correspond with which points, right? I'm sure we've all seen examples of that. In B, we have an improvement upon that, where it's very clear which labels correspond with which points. So all this just to say, be very intentional and deliberate about your placement of labels, okay? Same thing with callouts or labels for figures like this. So in the top example, we have some kind of randomly placed labels for these callouts right here on the left and right side. In part B, we've improved upon that by aligning all of the left-hand labels to this edge right here, and then aligning the right-hand labels along this curved edge right here. And we've gotten rid of these elbow connectors right here. We're just using straight lines for everything, with the exception of this down here. So just being consistent in your labels, consistent in your callouts, and the lines that you use to represent those labels can go a long way in improving the readability and legibility of your figure. Any questions about anything related to that? Okay. So the last thing I want to talk about in terms of improving effectiveness in a visualization is working with multidimensional data. So when I say multidimensional data, I'm referring to things like this, where we're working with a lot of different channels, a lot of different marks, and trying to represent or encode a lot of different attributes in the data set simultaneously. So in this first example right here, we have one dimension. We're representing our data in one dimension along our x position right here. We move to 2 dimensions here, x and y position. Here we've added color, and now we're at 3 dimensions. Here we've added size, and now we're at 4 dimensions. And then finally, we're at 5 dimensions when we add on top of those different symbol types. So we're often working on this end of the spectrum, right? Where we're trying to encode a lot of different attributes, a lot of different variables simultaneously in our figures. So there are a couple different things that you can do to improve the effectiveness of visualizations when working with multidimensional data. So the first thing we can do is to think about leveraging data storytelling when creating figures. So thinking about how to guide the reader through your data set in sort of faceted views one by one, and sort of help them understand what's going on in a very complex data set without showing them everything simultaneously at one time. So here's an example of that where some researchers have taken data about lung cancer and smoking and sort of partitioned that out into these different panels. And so these panels are like a story, right? You read them like a story from left to right in this sequence. And that story sort of tells you about what's going on in the data set, what the important points are for the user to really pay attention to, and sort of what kinds of conclusions they should draw from it. So we can use this idea of data storytelling in the figures that we produce in the same way. In addition to working with data storytelling, we can also use a variety of strategies for representing multidimensional data in 2 dimensions, because we're often working in 2 dimensions as opposed to more than 2. So these include things like using small multiples, context plus focus, filtering and faceting, and multiform encoding. So some of these things you may have heard of before. So these are small multiples. So this is a strategy where you take a data set that may be faceted across multiple variables. So this is an example that looks at stock prices over time. And you create multiple small versions of the same chart over and over again that all share a common axis. So in this case, the common axis is this time axis down here. So all of these charts, this one, this one, this one, all of them up the row, they all share this common time axis on the bottom. But they differ according to this particular category right here. So we call this small multiples, and it's a really easy way of improving the readability of multidimensional data. Another thing that we can do is use what's called context and focus, and use callouts to draw attention to particular parts of a data set in the visualization. So in this case, we would call the total, sort of the global view of the data sets, this global scatter plot back here, as the context, provides context for what we're going to zoom in on. And then we call this region that's highlighted right here, this yellow region, that's then blown up right here, the focus. So we can use this context plus focus strategy to really guide the attention of the viewer to a particular part in the data sets that we want them to pay attention to. We can also use things like parallel coordinate plots and scatter plot matrices to break out and facet a data set and sort of our views of that data set. So the top example here is an example of a parallel coordinates plot, which you may have seen. So in the parallel coordinates plot, we have multiple axes, vertical axes that correspond to different categories in a data set. And then every path that is connected across all of those axes corresponds to a single observation in our data set. Okay? So this is a parallel coordinates plot example for the famous iris data set that you've seen in R, I'm sure before. That's related to a scatter plot matrix, which looks like this down here. So in the scatter plot matrix, we have a bunch of different scatter plots that are arranged in a matrix format, hence the name. And the way that we read this is we take the vertical axis right here and the horizontal axis down here and match that to the corresponding cell in the matrix. So here, we're looking at sepal length versus sepal width. In this chart right here, we're looking at sepal length versus petal width down here. And then down here, in this chart right here, we have sepal width versus petal length. So it's a very compact, concise way of showing multiple scatter plots of the same data sets when you want to show multiple comparisons of pairwise variables in your data set. So scatter plot matrices and parallel coordinate plots. Very closely related to scatter plot matrices are things called trellis displays. So in this one, you do a similar thing where you facet out your data sets and your views of your data sets. So in this example, here's the original data sets where we're looking at different regions and age on the horizontal axis right here, and maybe political party affiliation and gender. And then on the right-hand side here, we partition that out across this left axis, bottom axis, right axis, and top axis. So we would read this in a way that's similar to how we would read a scatter plot matrix, by looking at whatever particular axes we're focusing on for the particular cell that we are zooming in on. So trellis display is another very compact way of representing multidimensional data. And then finally, we have things like multiform encoding, which is really just a fancy way of saying, take your data set and visualize it in multiple different ways. So in this example, we might do this to different effects. So for this data set right here, we've plotted it as just sort of as a standard scatter plot. And we might do that to emphasize the independence of points in this scatter plot. In this example, we've taken those points and we've drawn a line between them. And we might do that to imply or draw attention to the connections between the points. And then finally down here, we've had the exact same data set, and now we're representing it as bars. And we might do that to really emphasize that we want the user to do comparison across the different bars, across the different data points. So all these three different visualizations here, the exact same data set, but they have different effects, different perceptual and interpretive effects, depending on how we present them. Here's one more example of that. Here's the original data set right here, the sequence of numbers. Here we have represented those numbers in terms of these bin sizes. So we have these circle markers indicating the relative magnitude of those values and the size of the circles corresponding to those magnitudes. Here in C, we have another representation of the same data sets. Now we're looking at a distribution of the values across this axis down here. And then finally in D, we have another view of the data sets where we're highlighting this significance right here with this asterisk. So again, all these three different representations, and four if you include the original, have different interpretive effects, and we might use them in different contexts for different purposes. Okay. So again, these are basic ways that we can improve effectiveness in any kind of visualization through composition, color, clarity, and dimensionality. And a lot of these things might seem pretty intuitive, right? They might seem pretty obvious, but there are also things that we don't spend a lot of time thinking very intentionally about, especially when we're creating visualizations that we're making through software, and software does the work, the heavy lifting for us. So these are things I want you to think about as you move forward when you're creating visualizations of your own or critiquing other people's visualizations. And think about how those visualizations can be improved through these simple ways. Any questions about anything I talked about? Okay. So I'm going to give us a short break, about a 5-minute break, and then when we come back, we're going to spend the rest of our time doing some visualization critiques. So we're going to talk about how to critically evaluate visualizations across a few different axes. Okay? So I'll give you about a 5-minute break, come back right around 5 p.m. We'll get going again.
Thank you.